Blackwell is not a chip. Blackwell is the name of a platform. People think we make GPUs, and we do, but GPUs don't look the way they used to. Here's the, if you will, the heart of the Blackwell system. And this inside the company is not called Blackwell, it's just a number. And this is Blackwell sitting next to, this is the most advanced GPU in the world in production today. This is Hopper. This is Hopper. Hopper changed the world. This is Blackwell. It's okay, Hopper. You're very good. Good boy. Well, good girl. 208 billion transistors, and so you could see, I can see, there's a small line between two dies. This is the first time two dies have abutted like this together in such a way that the two dies think it's one chip. There's 10 terabytes of data between it, 10 terabytes per second, so that these two sides of the Blackwell chip have no clue which side they're on. There's no memory locality issues, no cache issues. It's just one giant chip. And so when we were told that Blackwell's ambitions were beyond the limits of physics, the engineer said, so what? And so this is what happened. And so this is the Blackwell chip, and it goes into two types of systems. The first one is form-fit-function compatible to Hopper. And so you slide out Hopper and you push in Blackwell. That's the reason why one of the challenges of ramping is going to be so efficient. There are installations of Hoppers all over the world, and they could be the same infrastructure, same design, the power, the electricity, the thermals, the software, identical, push it right back. And so this is a Hopper version for the current HGX configuration. And this is what the second Hopper looks like this. Now this is a prototype board, and Janine, could I just borrow? Ladies and gentlemen, Janine Paul. And so this is a fully functioning board, and I'll just be careful here. This right here is, I don't know, $10 billion. The second one's 5. It gets cheaper after that, so any customers in the audience, it's okay. All right, but this one's quite expensive. This is the bring-up board, and the way it's going to go to production is like this one here, okay? And so you're going to take this. It has two Blackwell chips and 4 Blackwell dies connected to a Grace CPU. The Grace CPU has a super fast chip-to-chip link. What's amazing is this computer is the first of its kind where this much computation, first of all, fits into this small of a place. Second, it's memory coherent. They feel like they're just one big happy family working on one application together. And so everything is coherent within it. Just the amount of, you saw the numbers. There's a lot of terabytes this and terabytes that. But this is a miracle. This is let's see, what are some of the things on here? There's NVLink on top, PCI Express on the bottom. On your, which one is mine and your left? One of them, it doesn't matter. One of them is a CPU chip-to-chip link. It's my left or your, depending on which side. I was trying to sort that out, and I just kind of, doesn't matter. Hopefully it comes plugged in, so. Okay, so this is the Grace Blackwell system. But there's more. So it turns out, all of the specs is fantastic, but we need a whole lot of new features in order to push the limits beyond, if you will, the limits of physics. We would like to always get a lot more X factors. And so one of the things that we did was we invented another transformer engine, the second generation. It has the ability to dynamically and automatically rescale and recast numerical formats to a lower precision whenever it can. Remember, artificial intelligence is about probability. And so you kind of have, 1.7, approximately 1.7 times approximately 1.4 to be approximately something else. Does that make sense? And so the ability for the mathematics to retain the precision and the range necessary in that particular stage of the pipeline, super important. And so it's not just about the fact that we designed a smaller ALU. The world's not quite that simple. You've got to figure out when you can use that across a computation that is thousands of GPUs. It's running for weeks and weeks on weeks, and you want to make sure that the training job is going to converge. And so this new transformer engine, we have a 5th generation NVLink. It's now twice as fast as Hopper, but very importantly, it has computation in the network. And the reason for that is because when you have so many different GPUs working together, we have to share our information with each other. We have to synchronize and update each other. And every so often, we have to reduce the partial products and then rebroadcast out the partial products, the sum of the partial products, back to everybody else. And so there's a lot of what is called all reduce and all to all and all gather. It's all part of this area of synchronization and collectives so that we can have GPUs working with each other. Having extraordinarily fast links and being able to do mathematics right in the network allows us to essentially amplify even further. So even though it's 1.8 terabytes per second, it's effectively higher than that. And so it's many times that of Hopper. The likelihood of a supercomputer running for weeks on end is approximately 0. And the reason for that is because there's so many components working at the same time. The probability of them working continuously is very low. And so we need to make sure that whenever there is we checkpoint and restart as often as we can, but if we have the ability to detect a weak chip or a weak node early, we can retire it and maybe swap in another processor. That ability to keep the utilization of the supercomputer high, especially when you just spent $2 billion building it, is super important. And so we put in a RAS engine, a reliability engine, that does 100% self-test, in-system test of every single gate, every single bit of memory on the Blackwell chip and all the memory that's connected to it. It's almost as if we shipped with every single chip its own advanced tester that we test our chips with. This is the first time we're doing this. Super excited about it. Secure AI. Only this conference do they clap for RAS. The secure AI. Obviously, you've just spent hundreds of millions of dollars creating a very important AI. And the code, the intelligence of that AI is encoded in the parameters. You want to make sure that on the one hand, you don't lose it. On the other hand, it doesn't get contaminated. And so we now have the ability to encrypt data, of course, at rest, but also in transit and while it's being computed. It's all encrypted. And so we now have the ability to encrypt in transmission, and when we're computing it, it is in a trusted environment, trusted engine environment. And the last thing is decompression. Moving data in and out of these nodes when the compute is so fast becomes really essential. And so we've put in a high line speed compression engine, and it effectively moves data 20 times faster in and out of these computers. These computers are so powerful, and there's such a large investment, the last thing we want to do is have them be idle. And so all of these capabilities are intended to keep Blackwell fed and as busy as possible. Overall, compared to Hopper, it is 2.5 times the FP8 performance for training per chip. It also has this new format called FP6, so that even though the computation speed is the same, the bandwidth that's amplified because of the memory, the amount of parameters you can store in the memory is now amplified. FP4 effectively doubles the throughput. This is vitally important for inference. One of the things that is becoming very clear is that whenever you use a computer with AI on the other side, when you're chatting with the chatbot, when you're asking it to review or make an image, remember, in the back is a GPU generating tokens. Some people call it inference, but it's more appropriately generation. The way that computing is done in the past was retrieval. You would grab your phone, you would touch something, some signals go off, basically an email goes off to some storage somewhere. There's pre-recorded content, somebody wrote a story, or somebody made an image, or somebody recorded a video. That pre-recorded content is then streamed back to the phone and recomposed in a way, based on a recommender system, to present the information to you. You know that in the future, the vast majority of that content will not be retrieved. And the reason for that is because that was pre-recorded by somebody who doesn't understand the context, which is the reason why we have to retrieve so much content. If you can be working with an AI that understands the context, who you are, for what reason you're fetching this information, and produces the information for you just the way you like it, the amount of energy we save, the amount of networking bandwidth we save, the amount of wasted time we save will be tremendous. The future is generative, which is the reason why we call it generative AI, which is the reason why this is a brand new industry. The way we compute is fundamentally different. We created a processor for the generative AI era. And one of the most important parts of it is content token generation. We call it, this format is FP4. Well, that's a lot of computation. 5x the token generation, 5x the inference capability of Hopper seems like enough. But why stop there? The answer is it's not enough, and I'm going to show you why. I'm going to show you why. And so we would like to have a bigger GPU, even bigger than this one. And so we decided to scale it. And notice, but first, let me just tell you how we've scaled. Over the course of the last 8 years, we've increased computation by 1,000 times. 8 years, 1,000 times. Remember, back in the good old days of Moore's Law, it was 2x, well, 5x every, 10x every 5 years. That's easiest math. 10x every 5 years, 100 times every 10 years. 100 times every 10 years in the middle, in the heydays of the PC revolution. 100 times every 10 years. In the last 8 years, we've gone 1,000 times. We have 2 more years to go. And so that puts it in perspective. The rate at which we're advancing computing is insane, and it's still not fast enough, so we built another chip. This chip is just an incredible chip. We call it the NVLink switch. It's 50 billion transistors. It's almost the size of Hopper all by itself. This switch chip has 4 NVLinks in it, each 1.8 terabytes per second.